Okay, good. The recording started now. Let me make a brief summary because about 20 days passed from the last lecture. So last time we discussed, we defined what is climate change and what are the main consequences. And it was just a narrative in order to emphasize and to explain to you what we are expecting from climate change. We also talked about uncertainty in our predictions, and we also started to talk about the science behind climate change, and we highlighted that it's a multidisciplinary topic. Today, I'm going forward with some more technical details on climate change, how to estimate climate change, and I'm moving to probably next lecture to first discussion of the health problem that may be caused by climate change. And I will try to be more quantitative this time because the purpose is to give you the tools or at least the information to make a quantitative assessment of the impact. So not just a narrative, but also a quantitative assessment by keeping the lecture at a not very detailed technical level. I make an attempt to make it very simple because actually it is simple, but sometimes, you know, when you go into the theory of several different disciplines, and especially if they are different from your background, it looks like the theory is really complicated. But actually, our assessment is not. So I will try to be, as I said, technical, but at the same time, very practical. So what I'm referring to today to start is the second link. We used the first link last time, introduction. Now I am clicking on the second one, the climate change problem. And as I said, this is an attempt to give a first quantitative assessment. This is my train of thought today. So let me see. Okay, I think, do you see? Yeah, you see full screen. So I will try to start by explaining to you the onset of climate change. So when climate change started, I will try to be quantitative, as I said, and then I will talk about climate forcings, sorry for the misspelling here, and feedbacks. And then I will talk about climate change attribution. So what are the causes of climate change? Because this gives the basis for discussing how we can mitigate climate change and adapt to it. Adaptation is probably our main focus. I will also briefly mention the history and the science of climate change with more details, and I will talk again about uncertainty in more quantitative terms, and I will define what tipping points are, tipping points in the climate system, because these are really a matter of concern. I then will talk about climate data, because they are the necessary information to make prediction for the future. If we want to make prediction of health impact of climate change on human health, we need to know how the climate will behave in the future. And therefore, we need to make prediction, and to provide support to prediction, we need data. And then I will talk finally of climate impacts to set the basis for discussing of the health impact of climate change. So let's try to move forward. We already defined what is climate change, but I also want to say, I want to start from the emergence of the sustainability concept, because climate change is strictly related to sustainability. Sustainability is a buzzword today, is a very popular term, but it is also very recent because, I mean, the concept of sustainability was brought to our attention no more than 40 years ago. And it was the second half of the 20th century, because in that period, you remember that we talked about the great acceleration. So people were enjoying really the economic liberalism. They were enjoying the economic expansion, the societal expansion. But then around the end of the 60s, communities started to realize that there were problems. Actually, in the United States, they started earlier. And there are many problems related to human activities, related to the sustainability of human activities, not only climate, there are many other problems. And to give you an example, here you see some pictures about, for instance, a retreat of glaciers, which is due to global warming. A retreat of glaciers that actually started around 1750, so about almost 300 years ago, but then became more evident. There was an acceleration after 1980. You see also on the right, on the top right, a picture of the Po River catchment, which is extremely important for the economy of Italy and for the welfare of Italy. And the picture shows the water balance in the catchment. The water balance, it shows some sustainability problems. If we account for how much rain we get from precipitation, how much water we get from precipitation, and we account for the withdrawals from surface water and groundwater, we see that indeed it looks like we are using more water than the Po River catchment takes. And probably this imbalance is compensated by the use of groundwater. And the groundwater is a topical issue because it looks like the replenishment time, the recharge time of groundwater may be some 10,000 years long. And therefore, it means that the water that we use now may take some 10,000 years to get replenished. And also, the Po River, we already talked about it. We see that the river flow is declining. And this is another sustainability problem, not only related to climate change, but related to the use that we make of that water. And also, you see in the bottom right, a typical climate phenomenon, which is the El Niño and La Niña. We don't talk about this phenomenon in details. I just want to say that these circulation processes in the southern Pacific basically are responsible for long-term cycles of climate, which create long-term, meaning cycles that may last for 5-10 years, which create sustainability problem. And what are the main signs of unsustainable impact of societal development? You see here some examples. Intensive agriculture. It's a food problem. It's a problem that is originated by our need for food. We have an increase of the population at the global level. We have local decreases, but at the global level, you know that the global population quintupled during the 20th century, and therefore we need more food. And also it's the societal development, the development of and the improvement of the welfare that requires more food. Actually, agriculture is impacting water resources and the quality of water resources, because on the one hand, we need water for irrigation, and keep in mind that 70% of the global use of water, of fresh water, is related to agriculture, to irrigation. And agriculture also needs the use of fertilizers. You know that we are trying now to decrease the use of fertilizer, but the problem is that fertilizer go into the receiving waters because after rainfall, the fertilizer is brought to the receiving water bodies and creates problems. The construction of dams, it's another sign of something that is indeed necessary. We couldn't imagine the welfare in Italy during the second half of the past century without dams. Dams are useful for saving water when it's abundant, to compensate our needs during droughts. They are useful for hydropower production, which is necessary. And they are also very useful in order to retain water during floods. So dams are indeed necessary to mitigate, to reduce the risk of flood, because when you get a flood, if the dam has some capacity left, the dam can store water and retain water, so decreasing the risk of floods downstream. But on the other hand, the dams have a strong impact, not only for the risk, because actually the risk today can be considered something that is very, very low. I mean, disasters like the ones that occurred in the past centuries are very unlikely to occur today. But they have an impact in terms of river flow depletion. Worldwide, there are several concerns related to river flow depletion because, for instance, the Yellow River, to give you an example, became in the downstream part dry for the first time in 1972 for the construction of dams that retain water, and therefore downstream there is no more water. And now the Yellow River in the downstream part is an intermittent river. And this has many health implications. When I talk about water quality that decreases or lack of water, there are many health implications, as we will see. Okay, and clearly this is a sign of sustainability. And the same problem occurred in the Colorado River. The Colorado River is heavily used with dams by creating artificial lakes. It's used in terms of water resources, which is fine. I mean, this is necessary. On the other hand, they had a measurement station in the very lower part of the Colorado River. They dismantled it in 1970 because they don't need to measure the flow in the Colorado River anymore because there was no flow, there no left flow. And therefore, we understood that we couldn't use all the water in a river. And the international community, the European Charter for Water in 1968, first introduced the concept of environmental flow, a flow that must be released downstream to protect the ecosystem. It's defined as a kind of flow that is necessary for the sustainability of the ecosystems, and the ecosystems produce a lot of services, what are called ecosystem services, which also have a beneficial effect on human health. And but the environmental flow very often it's a problem because we need that water, and therefore very often the environmental flow is disattended, is not provided, is not given because in emergency, when there are droughts, we need to use all the water that is available. I want to emphasize the fact that the concept of environmental flow, which seems to be obvious today, was introduced for the first time at the global level in 1968, which means that these concerns related to sustainability, ecosystem services, 50 years ago, didn't exist at all. They didn't exist at all. And another problem is the increased demand for energy. I don't spend much words on that because we already talked about it. But of course, you know that there are concerns related to sustainability of energy production, which is mainly ensured today by burning fossil fuels. And then there is the concentration of carbon dioxide, which is markedly increased. I showed to you a diagram 20 days ago. It's markedly increased during the 20th century, and such increase may be due to human activity, and in particular to burning fossil fuels. And carbon dioxide, the increased concentration of carbon dioxide, we think that is a main driver for climate change. So these are examples of the fact that indeed we have to be concerned about sustainability, not only for ensuring further development to our communities, but also for the welfare and for the protecting the health of people. Now, climate change, we already provided the definition, so I don't spend much time on this slide. And we already discussed the difference between weather and climate. And so climate change, the main, as I said, the main sign of climate change is the increase in global temperature. And we believe this is a fact, as I said. It's clearly something that is reflected by the data. It's something that we can estimate in about 1.3 degrees from the pre-industrial era, before the Industrial Revolution. It may look like something that is not very relevant, but let's try. We already said that actually warming is heterogeneous. Heterogeneous means that 1.3 is not the same everywhere, but there are areas, the so-called hot spots, where climate change, where the warming has been much higher. And so let's look here at this graph. which shows the temperature on the average over September during 10 years of several cities. And you see that in the cities, and this is one issue that I want to point to your attention, in the cities, the temperature increase has been much higher than 1 degree. So if you look, for instance, at Tokyo, you see that the temperature is increased, according to this graph, from about 21.4 to more than 24, so 3 degrees. Why is that? Because of the heat island effect, which is a local effect, which is caused by urbanization. So this effect, the heat island effect, is not caused by increased CO2 concentration, greenhouse gases. There is also this component, but the main component is the fact that in the urban area, you have less wind, you have more reflection of solar irradiance by buildings, by streets, and you have the presence of human activities that are causing heating, like air conditioning. Air conditioning, during the hotter months, we use air condition, of course, but you know that the air conditioner is emitting heat. Of course, the heat that is subtracted from inside the rooms is ejected in the atmosphere. And this is the result. You can clearly perceive this effect if you drive a motorbike or a bicycle and you enter into a urbanized area. It's clear, and it's recent. When I was a young children in the 1970s, I didn't realize that. And when I started driving a motorbike in 1980, also I didn't realize that. It was later that I could perceive really this increase of temperature. So this is something local. So one may say, okay, it's not a big problem because it's contributing to global temperature in a limited amount. On the other hand, people live in city. So health problems are caused where people are. And the majority of the population is concentrated in areas where we could have a temperature increase that is much higher than the average global. And actually, if you think of a 3-degree increase in a city, this may cause several health problems, from syncopes to heat stroke, etc. And indeed, this is a problem. There has been a recent contribution which is linked because it's open access. It's linked in my web pages. So let me open also the web page here. It's linked here. The web page, of course, with respect to the PowerPoint that I'm using, which is available for download at the end of the web page. So if you go to the end of the page here, there is okay, so I don't understand why is that, but anyway, let me just check. Let me do that, because I think that I should share the screen here. Actually, I have to share the screen, because if I don't share the screen, it's a bit of a problem. You don't see in the video what I'm showing. Anyway, let's now see if you see the web page. Just a second. Doesn't change. Oh, okay. So let me check why. I don't think it is really necessary that you see for now the web page. So let's try to move forward with this, and then I will solve the problem, because I think that to solve the problem I have to go out from the presentation and then you should see it. Yes, of course. Okay, so let me just click here. So in the web page you will see the same content of the PowerPoint, and once again, if you go at the end of the lecture, there is a link to the PowerPoint, but I suggest, as I already told you, I suggest that you use the web page, because the PowerPoint is, of course, a summary. And here there is a contribution that is linked, which is a open access paper. So this paper investigated the increase of temperature in several major cities of the world, and then they quantified the increase of temperature. And you see that here there are some numbers, like in some cities where most heat-related fatalities occur, the average change is about 0.3 degrees per decade, which means 1 degree per 30 years, which means in 100 years means 3 degrees, as I said. So the paper is providing additional information and is useful in order to refer to specific places. Okay, let's go back here and let me show the presentation. Okay, good. And here you can see a sketch of, the contribution is mentioned here in this slide. And there are the numbers. By the way, it's in some cities in East Asia and in Paris, in Moscow and Houston, they detected 0.6 centigrade degrees per decade, which means in 100 years about 6 degrees. So, I mean, it is something really important. And here you see the profile of the urban heat island. As I said, it's very local. You see that there is a drop of temperature in very significant if you go just outside. And this is something that you have to, maybe interesting for you. It can be, the heat island effect can be mitigated significantly by greening cities. And in fact, this is one of the adaptation measures that is suggested by the literature. Greening cities through green roofs, green walls, it's giving a significant contribution. This is why in certain places they are insisting on that. And also green roofs and green walls have also the advantage that they mitigate the flow into the sewer system, which is another sustainability problem. Because with increasing storm intensity, we are also experiencing, like in Milan, for instance, overflows of the sewer system, which is another problem also for public health. Okay, now it's important to try to understand a little bit better what are the forcings of this climate system and what are the feedbacks. It's important to try to gain some understanding of how the climate system works, because this allows you to be more confident or less confident on the predictions. When you understand a system, and you don't need to understand it in detail, but if you want to make a prediction of the climate impact on human health, you are in a much better position if you have the background to understand what a prediction is, understand what a climate scientist or a meteorologist say. So this is why I think it's important in this also second lecture that I give you some information. First of all, where does the energy to feed the climate system come from? From the sun. So the sun is the source of energy for the whole environment. And in particular, sun gives energy to the Earth system through the solar irradiance, which is defined as the power per unit area received from the sun. So the energy per unit area received from the sun. So it's measured in watts per square meter, and in the units of the International System of Measure. Keep in mind that we know a little about solar activity. So you may get some information from the media suggesting that we can measure solar irradiance in a very precise way. Actually, there is a lot of uncertainty in our knowledge of the sun activity. There is some knowledge that we gained. For instance, we gained that there is an 11-year cycle in the energy that is provided by the sun. And it's a cycle that is related to the activity of the sunspots. So the solar activity has this cycle of 11 years, and we could detect it because we have indeed some measurements of solar irradiance. They don't go back far in the past, but they go far enough in order to allow us to detect short-term cycles. So 11 years is a short term, is well covered by our measurements, and the measurements show that there is this cycle. But we don't know anything about possible longer cycles. And it is, if you're interested in getting global maps of solar irradiance, there is this link here, the Global Solar Atlas by the World Bank, which is interesting. It's widely used for evaluating the potential power that we can get from photovoltaic plants from the sun. So it is, of course, you know that there is now a strong push towards renewable energy. Is still provided a limited amount of the energy that we use. It's about 20%, 21% at the global level, but we are trying to increase it, even if we are aware of the fact that solar plants have an impact themselves. And in order to understand how much efficient can be a solar plant, we use these global maps. And so this, as I said, there is still a lot of uncertainty, and which means that we cannot make very long-term predictions. We can predict these 11-year cycles, but we cannot predict what will be the solar activity in 2050. So basically, the assumptions that is made by climate models is that besides these 11-year cycles, the solar irradiance is stationary, has the same behaviors that we observed during the recent past. But there is still some uncertainty on that, and this is indeed the power of our energy. By the way, it's the sun, the duration of the sun is not eternal. We know that the sun will end its life sooner or later, but the sooner is according to our knowledge, several billions of years ahead. Also, by the way, we know that life over Earth, even if the sun continued to provide energy, is not eternal, because the Earth system in our current configuration is not eternal. Now we know that Mars had an atmosphere, had water, and maybe had life. And the reason why now there is no more water on Mars, no more life then, is simply the fact that the nucleus of Mars became colder and colder, and at a certain point, the magnetic field ceased its activity. The movement of the material of iron in the nucleus of the planets, like in the Earth, is keeping the magnetic field active. We know that, of course. And without the magnetic field is like a screen that protects the atmosphere from the solar irradiance, which, if not filtered by the magnetic screen, causes destroys the atmosphere. So this is why now over Mars there is no more atmosphere. And also, without atmosphere, there is the dissolution of the molecules of water in oxygen and hydrogen, and therefore without the magnetic field. And this is why we think water disappeared over Mars. And the same destiny will occur over the Earth, of course, in billions and billions of years. This is important to know, because I think the concept behind the fact that the universe and the climate system are changing by definition, the concept is extremely important, because we are used to assume that the Earth system, the climate system, nature is like stationary, but it's not like that. There are forever changes, And probably the fact that there are changes makes also nature more resilient, because nature is used to changes. Okay, now the problem is that even if the solar irradiance is kept constant, the increase of greenhouse gases causes the reflection. The greenhouse gases reflect back the heat that from the sun goes to the earth, and the earth gives back to the atmosphere part of the heat, and this part that is given back gets trapped by the greenhouse. So the same effect is called greenhouse effect, because it's the same effect that you have in a greenhouse during the cold periods. CO2 is not the only greenhouse gas. It's also methane. Methane is extremely important. It's a very important greenhouse gas. And there are also other gases that play a minor role, but CO2 is part of the carbon cycle. And CO2 is released by human activities. So this is why we are concerned by CO2, because it's our main emission. On the other hand, CO2 is absorbed and released by the oceans. And it's not clear what is the percentage of CO2 that is emitted by humans with respect to the CO2 that is emitted by oceans. The oceans absorb CO2 when temperature goes down, and or let's see, the concentration, the limiting concentration, the concentration to saturation of CO2 in seawater is lower for increasing temperature. So when the temperature of water increases, the ocean releases the CO2 that has been stored. And as I said, what's important to point out is that it's not yet clear what is in percentage the effect of the CO2 emitted by humans. And this is very controversial. And I saw a paper that was published about 6 months ago showing that the CO2 emitted by humans contributes for 1/7, while oceans contributes by 6/7. This is a very controversial paper, very criticized, and there were requests to withdraw it, but actually the paper survived. It's still there. And this is a paper that gave a number, but giving these numbers, it's not easy, because we cannot measure the CO2 that is emitted by humans. We can estimate it, but we cannot measure it. But it is true that the CO2 concentration in the atmosphere increased a lot. And in the past 50 years, and we are getting close. We are now about at the level of 1.6 CO2 with respect to the concentration in the atmosphere, with respect to the pre-industrial level. And you know that there are predictions that we will reach the 2 CO2 concentration soon. Here in this graph, you see, let me see if it is visible, not much. Anyway, it's the CO2 emissions per capita in the vertical axis, depending on the GDP per capita, gross domestic product, which is, as you know, an indicator of wealth, an indicator of productivity, an indicator of income. And it's clear that there is a strong relationship. So the greater the development, the greater the GDP, and the greater the CO2 emissions. This is a graph that is given by Our World in Data, which is a free website. You can access it. You can use the graphs and without any problem. And there are also different colors for different continents. And also there is the detail of the United States and other specific countries. And now you see that the strong emitters are United States, Kuwait, the United Arab Emirates, and China is rising up sharply, which is, I mean, something that is perfectly normal. China is developing, and development means more GDP. More GDP, as we can see in this graph, means more emissions. They are strictly related. It's very difficult to mitigate this trend. So if we allow development, then the development may become unsustainable in terms of concentration. Sometimes we tend to blame the governments. Indeed, the governments can mitigate their CO2 emissions, but as I pointed out last time, this is costly. And sometimes the governments realize, in many cases, indeed, they realize that it's the resources that we have available now doesn't allow, indeed, to be very effective. So the target net zero by 2050, we are realizing now that it's something that is very difficult to achieve, and we will probably not be able to achieve it. And this is important because if climate change, in a way, cannot be mitigated, then it's clear that we have to shift our attention to adaptation actions. And in our case, adaptation means reducing, as we will see, the vulnerability of people and the exposure of people to climate change. Because if we cannot reduce the hazard, then we have to reduce vulnerability and exposure. No, it's solar irradiance is not constant. I said even if it's constant, the increase of greenhouse gases would cause an increase of temperature. But actually, it's not constant, and we know that there is this 11-year cycle, but we cannot make prediction of solar irradiance beyond this 11-year cycle in 2050. We cannot predict that. There are several models trying to do that, but they are not very effective so far. It is something that really we cannot predict. It could decrease the opinion of climate scientists is that it will not, because I think this opinion is also induced by the fact that they want to raise the attention of communities on the need for mitigation. Of course, we may realize in the future that we don't need to mitigate it because we may have decrease of solar activity. And, this is possible. On the other hand, if we want to take a precautionary approach, what they do, in a way, with climate models, they take the solar activity as constant. They are not increasing it. They take the solar activity as constant and make the prediction under this assumption. This is conservative. It's conservative because you are getting prepared. You are getting prepared to a situation which is likely to occur indeed. But on the other hand, if the actions, mitigation adaptations, are not sustainable, indeed this is a problem. And this is the main question: what should we do? And this is why, in many cases, we don't do anything, because it's hard to decide, and it's a decision in the presence of uncertainty. So, yes. Yeah, some example of adaptation. I mentioned green roofs. This is an example of adaptation.
Doesn't it also mitigate?
Mitigate. Another example, mitigation is different from adaptation. Mitigation means that you try to reduce climate change, you try to avoid it. And the only way that we know today to do that is by reducing emissions. But we know also that it will take some time. And it's not clear how long. But for instance, we have the experience of the pandemics where the emissions were reduced for 6 months. The emissions were much lower. But this didn't really make any effect on the global temperature. There was not a decrease. Actually, the current mainstream suggests that you need at least 30 years to get an effect in terms of mitigation. Adaptation is another story. Adaptation, you take for granted that temperature is increasing, that we will have like +2 by 2050, and then you try to reduce the heat island effect, try to improve the healthcare system in order to assist elder people. This means reducing vulnerability, or reducing exposure means that you migrate in countries where you support migration in countries where global warming is beneficial, because in the north of Europe, they are not concerned by global warming in general, because it becomes, they have more time for agriculture, they have plenty of water, so they don't have any big problem with the increased use of water resources. The problem with migration is an historical way of humans to adapt to changes in climate. We know that changes in climate occurred in the past, and the human reacted by migration and by migrating. The problem of migration is that it may take time, and a very fast migration causes wars, as we see today. When you have important fluxes of people from one place to another, you get wars. And actually, climate change looks like it is occurring quite rapidly. I think that today the main migration fluxes are not an effect of climate change. They are an effect of political tension. But on the other hand, there is a climate change component. And so this is one way to adapt. Migration is certainly one way. And okay, now let's move forward with feedbacks. The concept of feedback is extremely important. What is the feedback? The feedback are processes that can either amplify or reduce the effect of climate forcing. For instance, if you get an increase of temperature, which stimulates a further increase, like increase of temperature, I turn on the air conditioning, and this stimulates a further increase of temperature. This is called a positive feedback, a reinforcing feedback or positive feedback. A feedback that reduces an initial warming is a negative feedback. What is a negative feedback? An example, if you have more evaporation because of the increase of temperature, you have more clouds. More clouds means that the temperature is lower down. This is a negative feedback. So NASA provides a list of what we believe are the most important feedbacks on the climate cycle. One is clouds, which I just mentioned. They have an enormous impact over the climate of Earth. They are reflecting about 1/3 of the total amount of sunlight that hits the atmosphere. 1/3. So you understand that even small changes in cloud location, cloud extension, have a strong feedback over climate. So this is the first one. Precipitation. And precipitation, how will it change? Global climate models tell us that precipitation will generally increase due to the increased amount of water held in the atmosphere and the increased evaporation. Some regions may dry out, but in general, we think that precipitation in general will increase. More precipitation means a reduced temperature. So it is prevalently a negative feedback, but the feedback can be either positive or negative, but precipitation is indeed a feedback. Forest greening and browning. So natural processes like the growth of trees, they remove about half of human carbon dioxide emissions. So forests are the so-called carbon sink. We call a carbon sink a storage, a part of the Earth system that can absorb CO2. Now there is then a balance because, and there is a feedback because the human expansion caused diffuse deforestation. And this deforestation may contribute to further increasing the concentration of CO2 in the atmosphere. So this is another feedback. And you see that, okay, ice albedo. You see the graph on the right, I was saying, but let's discuss it later. So ice albedo. Ice is white and therefore is very reflective, in contrast to the ocean, which is dark and that absorbs heat. So with the limited extension nowadays of glaciers and areas covered by snow, then the ice albedo is a very strong positive feedback. Water vapor. Water vapor provides, it's the most abundant greenhouse gas. This is another thing that is to be taken into account. It is a feedback that amplifies climate warming. And because if you have more evaporation may contribute to amplify climate warming. The graph on the right is also taken by NASA and tells you that you have the water vapor plus methane plus carbon dioxide that cause the greenhouse effect, global warming, with the positive and negative feedbacks. You can see in the graph more feedbacks with respect to the 5 that I described. Just try to figure out in your mind how it works in general, this system, this climate system, which receives energy from the sun. Part of the energy is released back to the atmosphere by the Earth's surface, and then the heat that is reflected back is captured by the greenhouse, and with positive and negative feedbacks. If you understand positive and negative feedbacks, you have also an idea of what could be the adaptation measures. So say again, question. Yes, it is. If your question is what is the contribution of the water vapor in quantitative terms to the greenhouse gas, this is a very controversial question, and there is. Yes, yes, but indeed also the concentration of water vapor in the atmosphere is increasing. I'm not sure I'm answering to your question, but I think the information is also important. It's increasing because the atmosphere is warmer, and therefore you have a higher concentration. We have a higher concentration of CO2, but also a higher concentration of water vapor. I'm not sure if I answered your question. And it's this paper, this controversial paper that I mentioned to you, actually shows the aim of the paper is to prove that the effect. It is another one. Sorry. It is another one, the paper that aims to prove that the effect of water vapor is higher than the effect of CO2. Because there are interpretations which are highly questioned, which basically say that the temperature over Earth may have increased because for external drivers, not for drivers related to humans, like, for instance, an increase in solar activity, which may be an increase in solar activity that we can't quantify with the measurements, but there might be side effects that may have caused an increase, a slight increase. And then if you have a slight increase, and the ocean starts releasing more CO2, which causes a further increase. And then you have also an increase of the concentration of water vapor in the atmosphere. And we may have this kind of climate change, even if humans were not there, as it was in the past for the interglacial periods. I don't think we can say that the humans are not responsible. The humans are for sure responsible, because in any case, it's proved that our emissions increased a lot. This is a fact. And so we have a contribution on that. And the big question is, let's suppose that we now stop human emissions, we bring them to zero. So will climate continue, will warming continue at a lower level, but will it continue because there are also external drivers, or stopping emissions by humans would reverse the global warming? And this is relevant because our measures to mitigate the impact depend on the answer to this question. And also your measures for reducing the health impact depend on the answer to this question. Because, as I said, it's a matter of mitigation adaptation with limited resources. So this is what is described in this slide. The hypothesis is that the consequence, the conclusion is that we have to adapt. We have to focus our resources on adaptation. And just the hypothesis would be, let's forget about mitigation, but let's concentrate the resources on adaptation. I don't think this would be completely wise. It wouldn't be wise. Why? Because emissions have also an impact on the human health for other reasons, not besides global warming. So air pollution has been the first sign of unsustainability after the Industrial Revolution. When the Industrial Revolution occurred, in a matter of 10 years or a time span like that, the urban pollution was so high that the mortality of people increased. And therefore, we realized that air pollution was an issue. And then we started to care about it. You know now the measures in terms of health care against air pollution. So when the concentration of PM 2.5 increases above a certain concentration, a certain threshold, we stop the cars, etc. So it is, emissions are anyway something that we should possibly reduce. But of course, we have to understand what is the priority. Okay. For instance, economists say that now renewable energy is extremely impacting and costly. In 20 years, maybe that energy from hydrogen, now there is a lot of focus of research activity on energy from hydrogen. So maybe that in 20 years, we will be able to get energy from hydrogen in a very sustainable and cheap way. So the interpretation is, why should we dedicate a lot of resources now to solar energy, which it's not reliable because it's not available when we need it, and it cannot be stored. So why should we dedicate so many resources to that? We should better try to concentrate our effort on research over energy from hydrogen. So it is indeed a relevant issue, a relevant question. Now, this slide focuses rightly on this discussion, and in terms of natural variability. So the discussion is also natural variability versus anthropogenic contribution to climate change. So if it was solar activity causing climate change, this is natural variability. And in terms of that, here there are two videos linked, which we are not watching now. They are not long, they are like 6 minutes, but they are very illustrative. It's a narrative. One which discusses the evidence for the human contribution to climate change. The other one mentions the causes, the possible causes for similar changes in the past. And ice ages, I mean, the decrease of temperature during the ice age was -10 with respect to today. So it is indeed a big issue with the sea level that was 120 meters lower. So it's a big issue. And it proves that we may have, for natural causes, also shifting climates. shifts in climate. And it is not true, like we listen sometimes, that the pace of the current increase in temperature is unprecedented. We have proxy data that shows that in the past we had other cases of sudden changes of temperature. Good, time runs fast, so I would make a 10 minutes break. Do you have any question? No, I'm stopping the video now because I realized last time that if I leave the video open, even with the micro muted, there is the recording that is active anyway. So I removed the breaks from the video of last time. But now I think it's better if I pause the registration. So let's go to the presentation. This slide focuses on the history of climate change. It's not very important. I just want to emphasize once again that climate change is a recent concern. Sustainability is a concern that emerged earlier with climate change. As I said, in the Americas, in the United States, they got concerned by river pollution around 1920, 1930. And in reality, climate change came later. And it's quite curious, by the way, to say that around 1970, there were concerns about global cooling, because if you remember the graph of the global temperature, there was a kind of hiatus between 1950 and 1980. So, and there was a decrease, a global decrease of temperature. And so people became concerned about the global cooling. There is a Wikipedia page on global cooling, which is linked in my website. You may look at that if you are interested. And actually, now we know that the global cooling was probably caused by the increasing the concentration of aerosols, which also caused part of the aerosols caused the growth, the expansion of the ozone hole. And then everywhere at the global level, policies were activated to mitigate our emissions of aerosols. And this probably is related to the fact that the global cooling stopped. We were concerned about global cooling because actually, if you look at the past history of humans, you see that, I think I already mentioned this 20 days ago, we note that the expansion of the human civilization, of the human society, was much easier. So we had more expansion during warmer periods. For instance, in the Middle Age, during the so-called medieval warmer period, it was a period where probably temperature reached the level, today's level. And I say probably because we don't have measurements, we have only reconstructions. But during the medieval warmer period, there was an expansion of civilizations and an expansion of also of welfare, an improvement of welfare. And because during warmer periods, usually we have also reduced concentration of storms and floods. So in a way, during 1950, 60, and 70, when the measurements of temperature indicated a decrease, there was a widespread concern. And this is something that is interesting to note. So both the medieval warmer period and the global cooling, these are signs of variability of climate with opposite signs still within a stationary context, quite stationary context. Stationary means no significant changes in terms of statistics. And also, but another, I think, curious information, interesting information is that the greenhouse gas theory was developed, the concept, in the 19th century. So indeed, the Industrial Revolution must have given some incentive to the study of the effect of increased air pollution. Anyway, science of climate change is a multidisciplinary science. So let's, this is a slide that is reinforcing what we already discussed. Now, let's look at the science of climate change. It's interdisciplinary, and it's, as we discussed, it is a science where, of course, I am an engineer, so you may say that I am biased. For sure I am. It's a multidisciplinary effort where I think the role of engineering, especially in adaptation, is important. It's important because very often adaptation requires building infrastructures like dams, like hydroelectric plants or energy plants in general. And so, I mean, I think it's an important role. But the concept, which I really would like to emphasize, is this is a problem that we cannot afford, we cannot deal with within a single discipline. And this is the message that I'm particularly motivated to deliver to you. So depending on the health problem that you may think it's related to climate, I really would like to provide an incentive to you to seek the cooperation with the scientific disciplines that may be relevant to you. I don't think that in the medical sciences, the role of engineering intended as environmental engineering is really important, or structural engineering is really important. But for sure, there are other sciences that may be relevant, that may help you to get a good prediction, maybe climate science, a good prediction of climate change, and may help you to deal with uncertainty, that is for sure present in this topic. For instance, and to provide an example to you of why the multidisciplinary approach is important, I want to mention, and I want to discuss briefly, the possible existence of tipping points in the Earth system, but also in the human system, in the human body. What is a tipping point? A tipping point is a threshold value which, if trespassed, is overpassed, may cause a change of the state of the system that may be irreversible. Systems may have different situation of equilibrium. For instance, where we have a forest, we may have brushes. It does just depend on the initial condition, on the external conditions. So if we have conditions to ensure the growth of trees, for instance, we know that if we manage forests by cutting the brushes and supporting the growth of trees, once trees are grew up, they create a stable ecosystem, and brushes don't grow up anymore because the trees are basically dominating. But we know that if we cut the forest, then brushes start to dominate and they impede the growth of trees, which means that we have two equilibrium states, brushes and forests. And the same, I think, in the human body. I say I think because I'm sure I could provide an example, but in a human body, it's a system that may have different equilibrium states. And our problem is to identify these tipping points, to identify these different equilibrium states, and to identify what are the impacts that may flip the system from an equilibrium state to another equilibrium state. And because it may be irreversible. For instance, if you have, I give you one example, the Aral Sea disaster. The Aral Sea was one of the largest lakes in the world. And then around 1960, 70, there is a Wikipedia page on that. Russia started to withdraw water from the rivers contributing to the Aral Sea in order to irrigate the cotton. And what happened was that actually the evaporation from the Aral Sea was contributing to the local climate, therefore feeding the rivers. So they took water from the rivers and they diverted the water elsewhere. Evaporation from the Aral Sea decreased, and then the climate flipped to another equilibrium state, an equilibrium state where the river delivered much less water. So even if Russia stopped the withdrawal from the river, they couldn't re-establish the previous system. To re-establish the previous system, one should bring water to the Aral Sea, fill it up again, so re-establishing evaporation, and so re-establishing the flow in the river. But this is not possible because the sea is very large. It's not possible to bring water from somewhere else to there. So these tipping points are, we have a little knowledge of them. I provided some examples which we know, but does the climate system is the climate system characterized by tipping points that are still unknown? For instance, another example that I may make is related to the melting of the ice caps. We know that in the past, the Earth was without ice caps. Ice caps are there only during glaciations. I already mentioned to you that now we are in a post-glacial period, but we are still within a glaciation, and we have ice caps. We don't know in the past if the melting of the ice cap was slow or sudden. If it may be sudden, it means that there might be at a certain point a limiting temperature up there that, if passed, causes a sudden melting of the ice caps. Why sudden? Because we discovered only, I think, 15 years ago that under Greenland, under the North Pole, the North Ice Cap, there are a lot of hidden lakes, lakes that are encapsulated in the ice core. And they are still liquid because the pressure of the ice that is above this lens of water, it's very high, and the water doesn't get iced because of the high pressure. You know that if you put water under pressure, the temperature, the freezing temperature is decreased. And then what may happen, and in fact, there are a lot of research activities, they installed cameras because the researchers want to understand how these lakes suddenly are broken and water flows out. Because, of course, if the thickness of the ice coverage decreases, then the water is under pressure. It may happen that the bulbs of ice are broken suddenly. And as I said, there are a research project that, basing on video cameras, they hope to get a video of this rupture, of this sudden release of water from these hidden lakes. So it may be that in these lakes, we are now discovering more and more. Now that we have monitoring techniques that allow us to look in the deep ice core, we understood that there are several of them, and they may start to break in sequence and in a very short time frame. And we are looking in the past also in ice cores, in proxy data, in order to try to understand if in the past this melt was sudden or not. You understand that if we had a sudden melting of the ice cap in Greenland, this would cause an increase of sea level, for instance, that would be quite sudden and significant. Would be a significant increase, like 1 more meter, which is something that would be really, I mean, in a short time frame, would be really concerning. This is another example of tipping point. I think here there is this slide with discuss what I just mentioned to you, and even the IPCC, which is the International Panel on Intergovernmental Panel on Climate Change, it's an international institution that is formed by a selection of very top scientists. They recognize that tipping points remain uncertain, and the climate model do not take into account tipping points because the mechanism is not known. So if we don't know a mechanism, for many of them is not known, if we don't know a mechanism, we can't translate the mechanism into an analytical equation that forms a model. And these are some examples by the IPCC, and this is from Wikipedia, but I think it's based on a paper which is inspired by the IPCC. This is an example of tipping points that may happen. Another example of tipping point is the Sahara. And we know that the Sahara is now a desert, but it was green. And then once that it was transformed after a decrease of precipitation in an arid area, aridity caused a decrease in evaporation, change in local climate, no rainfall anymore. And so here you can see it's listed Sahara green because it may become green again, or other tipping points. In this case, the Sahara green again would be a positive outcome, but there are other tipping points that are listed here that, of course, you see Arctic sea ice loss, it's mentioned also here. And the presence of, the possible presence of tipping points is the reason of the concern, is the reason that brings people to be so alarmistic on climate change. Because if you look at climate predictions are not so concerning. I mean, climate predictions depict a hot future, depict a future with less water, but the amount of these changes is not something that may cause our extinction, may cause so big health problems. But the occurrence of a tipping point is something that is still unknown, still concerning. Of course, we cannot make a prediction of things that we don't know. We can't get concerned by any possible risk that we cannot quantify. But still, when we deal with climate impacts, this is something that has to be taken into account. And the concept of a tipping point can also be extended to society. So even societal systems, welfare systems, may have tipping points. And one example is the pandemic was a tipping point. It was a tipping point because there were changes. If you look at before the pandemic and after the pandemics, you see changes in many of our social systems. I wouldn't say that it was an environmental tipping point, but if you look at the societal organization, there was a big change. And some of these changes are actually shift from equilibrium state that was there before the pandemic to another equilibrium state. If you think about teaching or meeting or smart working, I mean, we were before the pandemic in an equilibrium state, no smart working. Those who were smart workers were just an exception in many countries of the Western world. Now we are at another equilibrium state, which we couldn't foresee before. We realized that smart working can be very efficient. We realized that teaching in streaming may be to some extent efficient. We are still debating that, but for sure we started some teaching in streaming, and it's unlikely that we go back. I would say it's impossible. This is something that I often say to my colleagues because some of them really hate teaching in streaming. I actually, at the University of Bologna, I teach about 50% in streaming, and I think it is fine. In my subjects, I think it is fine. This is an example of societal tipping points, and I'm sure that we know that also in the Earth system, there were changes that cannot be reverted. They are not all of them are positive, of course. There are indeed some situation now that if we compare to before the pandemics in terms of resources, in terms of healthcare, some situations that probably are not, we cannot say that they are improved, but we have to deal with them, and we have also to take into account these societal tipping points also in the economy. You know, there is for sure, if you look at, for instance, at the public debt, which is influencing the healthcare system a lot, the public debt has a threshold value. If you go above that threshold, there is the default, and the default is of the default of the state is something that cannot be easily reverted back. Okay, so now let's look at data, and here we start to become more quantitative. So if you want to devise adaptation measures for reducing the impact of climate change on the human health, you have to know what the climate in the future will be. You have to make predictions, and predictions are done with models. The models are optimized by looking at the past. So the model is conceived starting from a theory on how we think the climate works, and then we translate the theory in mathematical equations. These mathematical equations are flexible. The flexibility is given by coefficients, parameters. A parameter is a part of an equation, typically is a coefficient, which can be tuned to give flexibility to this equation. And how we adapt then the flexible equation to our needs by looking at the model capability to reproduce what we have observed. This is how the science works. Usually it starts from an experiment, and the experiment is the observation. The observation suggests that something is going on. The observations are the data. And then we elaborate a theory, and the theory is tested against the observations. So these data are essential. When we refer to climate science, I mean, it's in a typical situation. It's not a typical situation. Usually the model is really optimized to to reproduce what we have observed. In climate, we have limited data availability, and therefore the models are also optimized in order to match our belief in the theory. So if we believe that the climate is changing because of the increased CO2 concentration, we also optimized in climate science this capability of the model to respond with the increasing CO2 concentration with an increase of temperature. So this is optimization by belief in the theory rather than optimization against performances in reproducing historical data. And as I said, in climate science, we do like that because the data are very scarce. These are global models. In order to test them, you need data for all over the world. So it's really difficult to make a precise optimization. We call it also calibration or parameterization. So it's a bit atypical. If I look, for instance, at water resources, the problem is local, not global. So at the local level, it's easier in some situations to collect data. And therefore, hydrologists are much more rigorous in validating the models, testing the models. And once that you can test the model, you also get an estimate of uncertainty. Climate science is a bit atypical in that. So we have few data. So we optimize model also based on our belief. And we have more uncertainty. So there is, I can make you another example of the difference between optimization of a model by belief or by data. So if you think of a statistical analysis to estimate the probability of something, you can make an experiment. Like I want to estimate the probability of getting a head from tossing a coin. Okay, you make an experiment, you toss the coin 20 times, and you get an estimate of the probability of getting an head. So you count the number of heads, you divide it by the number of the total attempts, of the total tosses, and then you get a percentage. Like I got 50% head, and this is what you are going to get. But if you want to make a statistical analysis of the probability of a party to win an election, probability of a candidate to win a vote, you cannot make an experiment. You cannot make the election several times, and you cannot make an anticipated election. You have to, based on your belief, and this is what is called a Bayesian estimation. Based on your belief, you say, okay, I think candidate X has a probability of 60% to win. You may get some information like a small pool, like exit pools. This is an information that is supporting your belief, but still you have to start with the preliminary belief, like, and because the data from an exit pool are very small, so you have to include something more than that. When they make the exit pools, they integrate the result of the exit pool with some preliminary belief. But sometimes they are wrong. You know that exit pools, especially recently, they failed because of the uncertainty. Because when you estimate something based on your belief, there is more uncertainty. This is important to note, but still, I repeat, climate data are essential. And our first source of data is observations. They are not very long. If we look at temperature, we have observations since 1850 with the sufficient coverage because temperature is measured locally. You need many local measurements to make a global assessment. So we have sufficient enough global observations from 1850. We have temperatures in single location that go a little bit further back, but not much, like 200 years, up to 1750. For rainfall, we have observation, the longest rainfall series, I think there is a slide later on where I'm mentioning it, is the daily rainfall observations collected in Padua. And it started from 1725. Why people didn't start to measure earlier these phenomena? This is strange. People started to observe the stars 3,000 years ago, maybe. But they started to measure rainfall, which is very simple. You just have to put outside a tank, a bucket, and then every day you go there. You see if there is some water, you measure it. It's just with a ruler. It's very simple. But they started only in 1725. And there is one exception of the Egyptians. They measured the Nile for 600 years, the annual level, the annual maxima, for 600 years during their time. This is one exception, but otherwise, we don't have observations. Why is that? Probably because people didn't have the necessity to measure water levels, rainfall. They had the necessity to look at stars because they needed to get orientations during their cruises in the sea, the traders, and probably the Egyptians had this need because they wanted to make predictions because their lives depended on the Nile. because they needed the flooding for the fertilization with the mud of the River Nile of their fields, but an excess floods brought disasters. So they wanted to try to predict it. And they realized that the best way to predict it is to measure. So they measured with the Nilometer. It's very nice. If you look at this measuring instruments, it's still there at the Cairo. And if you look in Wikipedia, Nilometer, there are very nice pictures. They made measurements of the max level, a max annual, for 600 years because they wanted to make predictions. They realized that to make prediction, you have to observe a phenomenon and elaborate a model. But it was an exception. Otherwise, probably the humans didn't have the need to measure rainfall because they were concerned by other things. They were concerned by wars, they were concerned by tensions, and therefore they went to live up the mountains. And they were probably not so interested in, they didn't have this necessity. Actually, it was in Italy where people started. And I think the reason is that Italy is a country that is particularly exposed to weather extremes, to floods, to storms. And so I think this is the reason. And also the civilization in Italy was at that time, was very developed. So where do we find this data? Because we don't have many of them. This is an example of a, sorry. Let me just go back a little bit. I made a mistake in, you see on the screen that, yes, okay. I was here. I'm still going back. I am questioning with the keyboard, just 1 second here. I wanted to show this. This is the good daily rainfall series in Bologna. And here, because in Italy, it was not only in Padua that we started. So Bologna started to measure rainfall also during the 1700s. But there are gaps in the measurements before 1813. From 1813, the series is continuous. Here you see the annual levels and not the daily ones, because the daily ones is too dense. You cannot read it. So this is annual rainfall. First of all, look at the order of magnitude. It's around 800 millimeters. The average is a little bit less, about 700 millimeters. The blue line is the average, the long-term average. And this is the order of magnitude also of the annual rainfall in Milan over Italy. Over Italy is varying from 500 in the south to the most rainy region is Friuli, where they get more than 2 meters of rain during the year. Keep in mind this order of magnitude is important. If you want to understand the process, at least the basis, you have to get the order of magnitude. And what is interesting to see here, an interesting thing here is the fact that you see with the gray areas, the occurrence of long-term droughts. Sometimes it happens. We experience even recently in other continents, in Bologna not. You see, we don't have in the recent time a long-term drought. We had a single year that was very dry. It was 2003. It's somewhere there. And I think I can see it. And also, you see that overall, the recent time is characterized by a lower rainfall and a lower variability. But we didn't have a long drought. But if we look, for instance, here in Bologna between 1945 and 1950, 5 years with minus 25% of rainfall. Can you imagine? What implications also for the Earth system? Because you don't have water in rivers and the rivers get more polluted, so more bacteria, etc. And long-term droughts are relevant, I think, a relevant problem for the health of people. But okay, here the last one was from 1945 to 1950, but it may start again soon, because if something happened in the past, there is no reason to exclude that it may happen again. No reason. And if you look at recently, California, you listen from the media, a long drought from 1913 to from 2013 to 2017, 5 years. In South Africa, is more or less the same period. They got a drought that was 5 years long. Australia, from 2000 to 2010, 10 years of droughts. And they started a lot of desalination plants. They activated a lot of desalination plants because they assumed that the drought was lasting forever. And then they got, fortunately, rainfall like the pre-drought period, and now the desalination plants are not used anymore. So you see that it's important to plan the investment of resources in the right way. But the problem with observations is that we can't go back far in the past. This series is very lucky, but still, you see that, 1813, not much further. And the same if you look at rivers. For the Po rivers, we have observations from 1807, but we don't know anything before than that. So how can we resolve the problem here? An interesting solution is the use of proxies. And I'm sure you have heard about tree rings. The tree ring allow us to look back in the past much further, because there are trees that are like 400, 500 years long, some of them even more than that. So by reading the tree rings, we can understand that there were years where the tree grew a lot, and here's where the tree didn't grow up. And therefore, we can understand, we can relate climate to the tree rings, but not only tree rings. There are ice cores, there are cores from lakes. Limnology is helping us a lot here, because from the sediments that get accumulated at the bottom of the lakes, we can understand the past climate. And what is interesting here, first of all, how do we work with this proxy data? We take some observed data of the variable of interest, like temperature, and we study the correlation of temperature with these proxies in the instrumental period. So we have temperature from 1850, perfect. So we study the correlation, we study how much temperature from 1850 to today is related. Correlation means a relationship, a dependence, is related to the tree rings, for instance, or to other proxies. And then if we find a strong correlation, then we use this correlation to estimate the past climate beyond the start of the observations. So if we see that tree rings are related to rainfall, so that we can express, for instance, a linear relationship like annual rainfall equal to a parameter multiplied by the width of the tree ring. Then the width of the tree ring is available also for the past 500 years. We extend this relationship to the past, and we find rainfall in the past. It is a very interesting opportunity. Of course, there is uncertainty. So there is uncertainty in any measurement that you take, like in any statistics that you make for medical issues. There is uncertainty in any information, but of course, proxy data, and as the term suggests, are not like data. And therefore, we need to take this uncertainty into account. And what is, just 1 second, I move forward with the other slide, and then I show you a website, which I think it is interesting. And clearly, there is another opportunity for estimating the past climate, and it's related to the use of models. So climate models may be used to make future projections, but they may also be used to reconstruct the past climate. And there is the belief that the uncertainty of climate models may be lower than the uncertainty of proxy data, and to some extent also lower than the uncertainty of observations. Keep in mind that observations are local measurement. The climate model has a big advantage that the resolution is global. It has a global coverage with a very fine resolution. So the information they provide is more extended. Unfortunately, there is one problem. If you compare the climate reconstructed by the models, and I'm doing a lot of effort on that, and with a couple of PhD students, to compare the climate reconstructed by the models with the climate reconstructed with 3 rings and the climate given depicted by the observations. And the results are mixed. We are getting mixed results, but not only us. There is a lot of groups. There are a lot of groups in globally working on that. The results are mixed, depending on the time and the spatial scale. So what is the data we are looking for? It's daily rainfall, no way. Daily rainfall cannot be reconstructed, neither with the 3 rings, nor with climate data reliably. I mean, the climate model gives to you daily rainfall, but it's not a reliable reconstruction. Are we interested in annual rainfall? Okay, this is good. With 3 rings we can make a try. And also with climate models, it becomes a little bit more reliable. Or what is the spatial resolution? Are we looking to Bologna? So I made an experiment. Let's look at the time series of Bologna and compare with the climatic reconstructions. No way, it's not very good. But if you take the annual average, the annual rainfall averaged over Italy, then it becomes more reliable. So the results are mixed. And of course, climate models are our hope, because it would be fantastic if they were able to reconstruct the past climate and predict the future climate. It would be fantastic because they have global coverage. They have a fine resolution. Fantastic. They are our hope. But now, I published a paper just in July showing that we have to be very careful. Okay, and let me show you, but I need to move to the website because I have only one last slide for this topic, but I want to move here. This is not what I was looking for, but it's here. And this is the lecture from which I took the slides. You can see it, yes. And 3 rings, tipping points, climate data, here it is. I think I added a link. I modified this lecture just a couple of days ago. I think I changed also the date. And I included this link because, as I said, I'm a PhD student who is working on that, and it's great. He's really very active. And so he pointed to my attention this platform, which presents open access, a collection of proxy data that can be used to reconstruct past climate. I think it may be also interesting to you, so I just want to open it and show it to you. It's linked, so you can have a look at it. It's free, and it is very nice, this interactive map. So let's just wait a few seconds, which is showing a global map of the world with all the proxies that they have. And it is very easy to handle because, just one second, because you can make a selection of the kind of data that you want. For instance, corals, because also corals are an excellent proxy data, like speleothems. Speleothems are the caves. They have the stalagmites, and they have these structures which deliver a lot of information on the past climate, currently unavailable. I tested it yesterday, it was fine. Let me make another try. Launch interactive map. And 3 rings. So you have a map For instance, I made the selection of 3 rings, lake level, and many others. Some of them I'm not expert of. Pollens. Pollens are really interesting speleothems you see here. And if you deselect everything, for instance, and you keep only 3 rings, it shows to you the location of the 3 rings that they have, and you can get the data. So, I mean, this PhD student who did a very simple thing, he was interested in the reconstruction of river flows in the Po River for making predictions of future droughts, basing on past droughts. And I think it should update automatically. Let's see. But anyway, the 3 rings are the green dots. So he identified the 3 rings that are close to Italy. And he was just looking for a very simple linear relationship between the observed river flow in the Po River and the 3 ring width in that year. Linear relationship means a very simple relationship, like, as I said, annual flow equal to parameter A times the width of the 3 ring, and the parameter A is optimized. He selected the best value, and then he could define the reconstruction. And these data are easily accessible. If you click on the map, you know, now you see now there are the 3 rings here. And you see that the coverage is, I mean, of course, it's better in Europe and the North Americas, but also in Asia, there is quite good coverage. And of course, you can search for a location. So the map automatically zooms over the location, and you can get an idea of climate oscillation in the past. Just if you plot the 3 ring width against time, a long time, you get a good estimate of variability. This is a nice piece of information. There is also another interesting website which I want to show you because I think this information is useful, and it's you find it in my website. It is the Copernicus Data Store. Copernicus Data Store. Let me check. Yeah, Climate Data Store. And here you can find climate predictions and historical data. And for instance, we can make a data set. If we search for rainfall, let me see. Search. Soil erosion indicator for Italy, near surface meteorological variables from 1979 to 2019, and temperature and precipitation grid data for global and regional domains derived from in situ and satellite observations. And I think there is also, let's see, product type, climate projections. Let's click here. And climatic suitability for the presence and seasonal activities of mosquito for Europe derived from climate projections, etc. If I remove rainfall, I think here I should find predictions from global climate models. I see only CMIP5. Let me see if there is also the recent generation of models, CMIP 6. Here it is. Climate extreme indices and heat stress indicators derived from CMP 6, the most recent one, global climate projections. And this is a useful reference for you. The problem is that if you look for the data, you need some programming skills in Python to download the data. By the way, I am interested. Do you have a background in computer programming in whatever language, or no? Okay. This is interesting because ocean engineering, it's not a very consolidated background. Unfortunately, to use this data, some of them one needs some coding skills. So this is indeed a bit of a problem. But I can also point you out another link, which is interesting, which is the CMCC climate projections over Italy. This are easy to use. And this is not yet linked in my web pages, but I will link it. Okay. Let's see. I think here. Italy in a changing climate, kilometer by kilometer, the new open source data from CMCC projections. This is very useful because it gives to you maps. For instance, if you are interested to know the predicted temperature in 2050 in Italy, you can find a map here. And these are very easy to use. So I think it is here. Okay, data sets. Let's see. Climate projections, downscaled over Italy. I think it is this one. There are several different topics. This is downscaled. They differ from the resolution. This is a resolution with a high Hague kilometers square grid. This one is downscaled at 2.2 resolution. So here are the maps, and I think this is one. Let me just see. Okay, you can select all the temporal coverage. Let's see if we select all, what happens. Anyway, if you play with this website, you find out a map, which is shown here. Just 1 second, license. Okay. For instance, here there is a precipitation millimeters per day. It's the anomaly in precipitation. And this map shows, I'm not sure to which period, this is just an example, but you can extract specific maps by just playing with these selections. I don't want to play now because it takes too much time. But if you play, you get maps like this one. This shows to you the changes in precipitation, millimeters per day, over Italy. And where it's blue means that it increases. Where it's red or tending to the red, it means a decrease. We know that precipitation in Italy is predicted to decrease in the south and increase in the northeast. And these are maps that are useful because you can get what you need is not a precise prediction, I think, for your need. You need an indication, you need an order of magnitude. And I think these are good. Let me show you the last slide. And then we make a second break. Climate impact. This is my last slide on this topic, and then we shift to health problems. So your field where I may also learn something from you. Climate impact. This shows to you a final consideration. And the final consideration is given by these two graphs. So you see on the top graph, the global losses from weather disasters worldwide from 1980 to 2020. You see a clear increase. These are losses, economic losses. But if you divide the economic losses by the global GDP, gross domestic products, you get a series that is more or less stationary. So let's be aware of the fact that the impact of climate change depends also on the economic value of the assets that are exposed, depends on the state of the health system, if we look at human health, depends also on the exposure of people to the changes. And we can use a very similar approach to estimate the risk for the human health and the risk for society, the risk of flooding, for instance. It's a very similar approach, which I'm going to introduce in the next series of slides. Okay, let's make another break here. Okay, so next link. So we are getting into climate change impact on health, into the topic, the core topic. And then my prediction is to talk about specifically next, I'm not sure whether next time or in the last lecture, to talk about climate-related diseases with the attempt to be more specific. But let me start with this one, which is a PowerPoint presentation. And we need to start the PowerPoint presentation to get the animation going. This is, this is a presentation from the Center for Disaster Preventions, and you see at the core, at the center of the animation, will stop with all the details. It's just a nice movie to get your attention, but you will have time to read everything. So at the core, at the center of the circle, in the inner circle, you see climate change, which is resembled by heat, the sun, the red sun, and then storms, the cloud with the thunderstorm, and water, because also floods and droughts are the most relevant impact. And the fourth icon, actually, I don't understand whether it's energy or something like hurricanes. Actually, what are considered to be the most effective impact of climate change on Earth are considered to be originated by mainly increase of temperature, floods and droughts, extreme wind and storms, and hurricanes. There are several other effects of climate change that may have an impact on Earth, but these, which I have just listed, are considered to be the most important. And then you see the effect of these four drivers: rising temperature, it's the circle that is moving, more extreme weather, rising sea level, and increasing CO2 levels. And these changes then originate the specific sources of impact: air pollution, changes in vector ecology, vector-borne diseases, increasing allergens, water quality impacts, water and food supply impacts, environmental degradation, extreme heat, severe weather. And then you see the diseases in the external part: asthma, cardiovascular disease, also called CVD, the acronym, and then the vector-borne diseases: malaria, dengue, encephalitis, hantavirus, Rift Valley fever, Lyme disease. Lyme disease is considered to be very impacted by increased risk after climate change, chikungunya, and West Nile virus. And then for the allergens, respiratory allergies, asthma. For the water quality impacts, cholera. This is a well-known impact of poor water quality. Cryptosporidiosis, sorry for my pronunciation, Campylobacter, leptospirosis, harmful algal blooms. For water and food supply, malnutrition, diarrheal diseases. And for environmental degradation, forced migration, civil conflict, mental health impacts. These are considered to be more and more affected by climate change. Indeed, I realize that there is a widespread concern due to climate change, induced also by the tones with which climate change is presented by the media. And indeed, I see, even personally, several examples of people that are much concerned. So the mental impacts is maybe related to traumatic experiences, like a person affected by a flood, for instance, but it may also be related with increasing frequency to this concern that induces a lot of stress. And you can see also the outcome from this concern, the movement of Friday for Futures, the movement of Extinction Rebellion. They are protesting, they are blocking the traffic in the streets. And I mean, this is indeed the cause of health impacts, mental health impacts. For extreme heat, we have heat-related illnesses and deaths like syncope, cardiovascular failure. For severe weather, injuries. This is another relevant impact of climate change on the health of people. Fatalities, mental health impacts, again, after a traumatic experience. I think this picture is providing a very nice overview. So this is taken from the sources indicated here. I go back 1 second to my website. It's taken from the Centers for Disease Control and Prevention. And this is a governmental center. I think it is, I don't remember if it is United States or you can easily check with Google, United States or Australia. But it's a governmental center for disease control and prevention that is dedicating a lot of information to the impact of climate change on public health. You may visit the website because there is really a lot of things, a lot of information, part of which I used because it's also open access, it's public domain. I used for compiling the next lecture, the next link, let's say, the next link, the web page. So I think we can close this, but it gives to you an idea of what I'm talking about in today and next Thursday. So let me close this and let me open this one. And here, if you go down, there is a PowerPoint, which I am opening now. Okay, let me put it in presentation mode. This is the summary. My train of thoughts for this lecture. Today, I will continue for 20 minutes more, up to 6:15, more or less. Classification of climate impacts, ways climate affects human health through floods, droughts. I gave an anticipation with the slide that I just presented to you. State of global health, because it's just a very brief perspective to provide the initial condition. And it's a perspective that is presented by the IPCC. So it's a perspective from climate science. So I think it is interesting. It is very short, by the way. And then impact assessment. And this is something that is becoming a bit quantitative. So risk analysis in order to estimate with numbers the risk induced by climate change on specific diseases, but it's not very technical. So I reassure you, it's a bit quantitative, but not very technical. It's very easy to be understood. By the way, I was looking for a blackboard, but I think I can use this. Probably it's Touch. It's Touch. Okay, very good, perfect. And I can use the pen. Maybe next time I can use it. Okay, and then we will see that impact assessment requires the estimation of hazard, vulnerability, and exposure of the population. Hazard means how likely it is that something occurs. Flood hazard means to estimate flood hazard means to derive a quantitative measure of the likelihood that a flood occurs, and this is influenced by climate change. Of course, we believe that it's more likely that we get flooded under climate change. And this is hazard estimation. Vulnerability, it depends on the state of the mitigation measures. So when we say that a community is vulnerable, means, for instance, that the Earth system is not organized enough. So vulnerability means that if a person is exposed to the risk of getting an injury after climate change, the person is exposed means that the person is exposed to a flood means that the person can be indeed flooded. So vulnerability means that instead, if the person is flooded, what is the amount of the consequence of that? So a person may be flooded, but if the house is flood proof, the water doesn't get into the house, so there is no impact. If the person is exposed to the flood occurs, and the person is completely unprotected, the person is flushed away by the water, this means that vulnerability is maximum. So vulnerability measures the level of protection. And then we will get into the details of hazard estimation, vulnerability and exposure estimation. And we will see that it's important to identify, to assess vulnerability and exposures, what are called the health determinants of connected to climate change. So temperature is an health determinant. If the temperature gets very high, it's a problem. It means that exposure increases and also vulnerability may increase. And then we will talk also of the health benefits after climate change, and then we will draw a synthesis. When we talk about risk assessment, you see a different perspective in different disciplines. And I realized that starting from my experience as an engineer, I realized that if I talk to a structural engineer, their assessment methods for risk after an earthquake is different from my approach of estimating the risk of flooding, and flooding is my field. I realized, getting prepared for these lectures, that in medicine, there are several approaches which are a little bit different, but with something in common. So I thought it was very interesting for me to understand the different taxonomy, the different definitions, and the difference in methods. And I think it is interesting to compare them and to try to elaborate a synthesis. This is why I close with critical synthesis, trying to bridge the experiences of the different disciplines that are involved in this problem. Okay, so some obvious premises. Climate is a fundamental driver of environmental condition, and it is then much influential on the health of humans, which depend on the environmental condition in a first instance. Then the health of humans also depends on other issues. But of course, we know that, for instance, when there is a lot of humidity, there is the risk of getting vector-borne diseases, and higher risk. We know that when the temperature is higher, there might be changes in the ecosystems with an increase of the ticks, which spread the Lyme disease, for instance. We know that, and for this reason, I say this is an obvious premise. Let's take into account that through evolution, climate and physical condition of individuals co-evolve, so that the physical condition of individuals gets adapted to climate. And so what does this mean? It means that now our body is adapted to our current climate, and our body reacts if there is a change in climate. And we can make, through evolution, several examples. So if we have a change in climate, of course, we have to expect a corresponding adaptation of individuals. And such adaptation may require some time. And if the time scale of adaptation is not the same time scale of climate change, then we are likely to get adverse consequences. And for instance, if the temperature increases, we might expect that the body of the people is not prepared to that, and they may suffer more from syncopes or heat stroke. After global warming, indeed, this is a concern. After global warming and the related further changes in climate, Thanks. See you next time. So, medical issues caused by natural disasters, such as floods and hurricanes, may be associated with the physical trauma. And this provides to us a first classification. We may split the impacts of climate change on health between physical traumas and issues not related to physical trauma. This is an important difference because the physical traumas are actually easier to estimate and assess. And we know how many people died after the Vajont disaster, which is not really related to climate. But we know, for instance, other events that may be or probably are related to climate, like the flood in the Marche region last year. And we know the number of people who died, the number of people who were injured. This is quite easy. The other impacts, non-physical traumas, are a little bit more cumbersome to assess, to estimate, and it's not easy. And for instance, cardiovascular diseases, which may also be amplified by a shock, or respiratory diseases, or vector-borne diseases, it's not easy to relate them to climate. For instance, you know that there is a debate nowadays, and some very famous researcher with a lot of reputation, with a high reputation, say that maybe that the COVID-19 was related also to climate change. Also, Ilaria Capua in a TV debate which I watched, said that she cannot exclude that maybe the higher temperature may have in a way contributed to this jump of speeds. I'm not sure whether this is a correct English translation. Let's assume that it was caused by this this jump of species from an animal species to the human species. And she said that she cannot exclude that. And what I just discussed gives to us also an idea for a further classification. We may classify the impact of climate change on human health in short-term impacts like traumatic injuries and long-term impacts. There are impacts indeed that may become evident, may become clear after a long time. If you think at mental disorder, for instance, this is typically an impact that is not a short-term one, and it comes out in the long term, and this makes assessment indeed more difficult. What we already know is that indeed the effect of climate change is the product of a complex mechanism where there are several drivers. And so let's try to better understand. So what are these drivers? Local climate variations. For instance, we already mentioned that in cities, the risk of adverse consequences related to increasing temperature is higher. And also it depends on the climate variables that are relevant, because if we speak of temperature is one thing, if we speak of floods is another thing, if we speak of droughts, it's another different story. And once again, local conditions, socioeconomic context, the state of the healthcare system, and accessibility to healthcare, and water security state, it's extremely important. So do people have easy access to water, agricultural production and techniques, the local features of population like the age, extremely important, and nutrition, health state of the people. So this is why we talk about the state, the global state of health, and the presence or not of climate change adaptation policies. In a quantitative assessment, we have to find a way to take into account these several mechanisms, either by trying to model them explicitly or by making assumptions. Remember that you can always make a prediction and compensate the lack of information with assumptions. You should be able to support these assumptions with evidence, if it's possible, or theory. But assumptions are something that is really important and useful. So sometimes we get criticized because some people question our assumption. They say, okay, but I understand what you say, but it's you are relying on assumptions. I don't think there is anything wrong in relying on assumptions, provided they are clearly stated. Now, this figure is providing a first sketch of the mechanisms that we have to decipher. So we have climate change on the left. I try to stand up because it's otherwise there is some resonance. And you see that we list here the four drivers, the fourth climate variables, the four, which we believe are important. And there are no hurricanes here, depending on, this is an IPCC figure. So it's taken by the, I think it's taken by the fifth, the fifth assessment report of IPCC. IPCC, as I told you 20 days ago, is releasing periodically reports. And this is, they started from the first. The first was issued, I think, in 1999, or maybe a little bit later. And the last one was issued, is still being issued, but some chapters were issued early this year. It's the assessment report number 6. And this figure is taken by the assessment report number 5. There is a lot of information in these reports which are available open access. And you have the links in my webpage if you're interested. And in the fifth assessment report, there is an extensive treatment of health impacts. I found it a little bit trivial. First, if you look for references on health impact of climate change, what you find is still in the domain, in the realm of research. And so I looked for the scientific papers, and it's still not very organized. So it is also interesting for this reason. And I found that most of the references are not specific. I also try to look at the literature in medicine. Many of them are not specific. I just wanted to make this premise. I tried to make my best selection, and you will see that we will go into quantitative terms to some extent. Anyway, climate change, you see that they consider as variable precipitation, heat, floods, and storms. So one may say that hurricanes are missing here, and depending on the source, you may find other variables which are in turn considered. And then you have a direct relationship between these four variables and the health impacts. IPCC considers only undernutrition, drowning, which means flooding, and heart disease and malaria. And basically, it's a mix of vector-borne diseases and traumatic diseases and diseases related to water and food, undernutrition, and also malaria to some extent. So there is a direct link, but in general, there is a mediation which is operated by the environmental condition, the social infrastructure, and the conditions of the public health system. As I said, IPCC in AR5 gave a lot of consideration to the health impacts. In AR6, not much. Maybe that something is published in the reports that will be published later, because they are not all published. Not all the chapters of the AR6 are published. But now at present, I found that it's most quantitative, the reference of the AR5. And you see that in terms of environmental condition, they mention the geography. Geography means geographical location, means the morphology of the land. If the land is a mountain land rather than a lowland where you may have the problem of humidity, the presence of marshes, which are favorable to malaria, to other types of vector-borne diseases. And then the baseline weather, of course, because it depends on the initial conditions, in this case of the weather. Also, they list soil and dust because the type of soil may be very influential. And I give you an example. The Dust Bowl that occurred at the end of the 1930s in the United States. If you look in Wikipedia, it's a very interesting story. Dust Bowl was originated by a drought that dried the soil, and the soil was very incoherent. So after windstorms, a dust bowl was originated, a dust storm, which was triggered by the soil condition, the wind, lack of precipitation first, dryness, wind and soil condition. The presence of vegetation, baseline air and water, of course, baseline condition of water, quality. And then the social infrastructure. So direct exposure, flood damage, direct exposure to flood damage, storm vulnerability, and heat stress. The impact actually depends much on the social structure. Do they have air conditioning? No, no way to get air conditioning, then the impact is larger, of course. And then indirect exposures through natural system, allergens, disease vectors, increased water pollution, and economic and social disruption. So food production, distribution, mental stress. Public health capability, this is an important side. Warning systems, socioeconomic status, which means public debt. So the public debt is very relevant. This is a problem because if it's very relevant, there is no possibility to make investment in adaptation. Health and nutrition status and primary health care. And we have to understand how these mediations jointly play together to determine these health impacts. Because what we need to understand is whether there is an impact, whether it is significant, and how we can work on it. To conclude for today, but this presentation, you see, it's much longer. Just let's have a look, and then we start again next week from this. At the annual incidence of Lyme disease in the United States from 1991 to 2018. And you see several graphs of this type. The Lyme disease, as I told you before, is considered to be indeed severely impacted by the climate change, and in particular by the increase in temperature, which means that the life cycle of the ticks is expanded, which means that we are more exposed, and therefore we have to counterbalance with reduced vulnerability, because this is an hazard that is already materialized. We are more exposed. If we want to keep the risk at a constant level, we have to compensate by reducing vulnerability, which may imply use creams, use repellents, using limiting our permanence in the outside when there is the risk, and this means adapting by reducing vulnerability. That's it for today. We are meeting again next Thursday. The room in your calendar is again this one, or? Okay, now I